Acid-base balance, a chemical experience. Everybody's nemesis, nobody's friend. Poor acid-base. Here we are, Path, Chapter 6, Part 3. This is Dr. DeShavo. As always, if you have any questions, shoot me an email. Let's get right into this. So, please watch my video. I have a summary that I have uploaded into your media supplements. I think it's helpful to hear it in multiple ways. Review it. I go over respiratory, metabolic, buffers, and pH balance itself. So a lot of it's probably going to sound familiar, but I just thought it would help to have my video. So pH is that scale on the pH scale according to the concentration of hydrogen ions. And I will show you that scale in a few slides. But a good thing to know is normal systemic serum pH and interstitial tissues are this range too, is 7.35 to 7.45, okay? And if we're talking about the inside of the stomach, it's going to be way more acidic, for example. So we're talking about in the bloodstream and in the tissues of the body. Excuse me. Body fluids, kidneys, and lungs help to maintain balance. These are going to be the three big players that we're going to talk about. Subtle changes can cause serious effects. Your pH scale is 0 to 14. Our normal range is only 7.35 to 7.45. It's very, very small. So if we have a huge shift, we can cause a lot of problems. So pH reflects the hydrogen concentration, and hydrogen is H+. It is a very strong acid. So the more the hydrogen, the lower the pH. So if we get down to 2, it's going to be pretty low. If we get up to 14, we're going to be more basic. So systems that work to maintain acid base are the buffers that we find in the bloodstream, for the most part, the respiratory system, and the renal system. Some people reference or put the renal system in with metabolic. Metabolic also includes, serum issues such as ketoacidosis. Some people link that in together. But when we talk about metabolic, we're really going to be talking about renal because that's going to be the main driver. So here's our pH scale. Acidic is on the left, so that'll have a higher concentration of H+, which is hydrogen ions. If we look to the far right, it is more basic at the highest level of 14. There actually is going to be an increased amount of hydroxyl ions, which are OH negative. You don't even need to remember that, but I do want you to look. If you put H+, just as a little side note, H plus OH negative. You actually cancel out the positive and negative. You remember that from chemistry. I'm not going to test you on this, but I just want you to be aware of it. And then you combine them together. Guess what we get? H2O. That is correct. But our body will break H2O apart to get these ions because we actually do use these ions in different areas of the body. But just as a sidebar, excuse me, the normal neutral for blood and tissues will be in this range. And then like I said, if we're talking about like stomach acid, we're going to be closer to 2, for example. So there are some other general pH levels in the body, but the majority of the body is going to be right smack in the middle. Now, buffers help to maintain normal pH, and buffers are in place to basically sense if we're getting too acidic or too basic. And it causes an immediate reaction in response to those changes in pH. The changes in pH, guys, happen all day long. Our body is constantly going one way or another. The buffer systems help to maintain a normal pH. There are 4 that your book lists. The biggest one that I usually teach about, and I have in my video if you want to watch it, is bicarbonate carbonic acid system. It's a series of substances that are right in your bloodstream that are ready to either absorb hydrogen ions or release hydrogen ions, depending on whether we're getting too acidic or too basic. Okay, so if we're getting too acidic, it'll absorb hydrogen ions, thereby decreasing the acidity, because remember, hydrogen is what drives that acidity, or it'll release hydrogen ions if we're too basic. Okay, phosphate system, hemoglobin, and protein system, we're not even going to get into those. Your book lists them. The main one that we're going to talk about is bicarbonate carbonic acid system. And we aren't even going to get into details. This lecture was just too long anyway, but realize bicarbonate carbonic acid system will help to regulate pH levels if they're getting too acidic and too basic. And if you want to know the details, like I said, I've got that in my other video. Question time. Buffer systems in the body help to maintain a normal pH. What do you think? All right, moving on. So respiratory regulation. You need to remember CO2 is acidic. If we keep too much CO2, we will have a respiratory acidosis. If we get rid of too much CO2, we'll have a respiratory alkalosis. So this could be a primary condition where we have a disease of the lungs with respiratory acidosis or alkalosis. For example, emphysema, we retain too much CO2. In respiratory acidosis, we retain too much CO2. We become more acidic because of that disease of the lungs. As opposed to the respiratory system creating a compensation mechanism, such as with diabetes. With diabetes, if your patient's not regulated and becomes too acidic, we can get rid of CO2 to compensate. And we'll get into compensations in a little bit, although that's basically the sum of it. So if we speed up respirations, we'll excrete more carbon dioxide. If we slow down, we'll retain it. Now, your body normally, even though you can control your breathing, your body normally regulates your respiration, and it does that by monitoring the amount of CO2 in the blood. And there are chemical receptors that monitor CO2 called chemoreceptors. If CO2 increases too high, we'll increase our rate and rhythm of respiration. If CO2 is too low, we'll slow it. And it all happens on its own with the medulla and actually part of the pons. Renal regulation. So the thing to remember, and you could jot this down in the notes here, is the kidneys, I think, oh no, it's right there. The kidneys will balance hydrogen and bicarbonate. So what it will do, hydrogen is acidic, it's that H plus ion that we've spoken about, and bicarbonate is basic. With the kidneys, they will be the opposite of each other. If we excrete hydrogen, we retain bicarbonate. If we get rid of bicarbonate, we retain hydrogen, because they have the opposite effect. If our body is too acidic, we will get rid of hydrogen and retain bicarbonate. If our body becomes too basic, we will get rid of bicarbonate and retain hydrogen. One more time. If our body is too acidic, it will get rid of hydrogen and retain bicarbonate. If our body is too basic, it gets rid of bicarbonate and retains hydrogen. Your kidneys are going to try to regulate your systemic pH by doing that. Okay? It responds slower than the respiratory, but it lasts longer. So together they make a pretty good team. Now, compensation, I mentioned. The body never overcompensates, okay, because it's going to monitor on a regular basis and compensate only to the level it needs to. The kidneys will compensate for either the lungs or if we have like a ketoacidosis in the bloodstream. And we see that, a good way to remember that, okay, is, well, That's more with the respiratory rate. A way to remember the compensation with ketoacidosis is if you have a buildup of that acidity in the bloodstream. We've seen this with people who are diabetic. They increase their rate and rhythm because they're trying to get rid of CO2, okay, to compensate for that. So that's a good example. So a good thing to remember with compensation is one of those mechanisms, either the kidneys or the lungs, are going to compensate for another system that's creating an acid-base imbalance. So the kidneys will get rid of hydrogen if we have too much carbon dioxide, right? The lungs will get rid of CO2 if we have ketoacidosis. If the kidneys are failing and can't get rid of hydrogen, you'll increase your respiratory rate. So compensation will be the other organ that is not the primary damaged one, okay? Whew, that's a chunk of change. So if the problem causing the pH balance originates in the lungs, the kidneys will try to correct it. If the problem originates outside of the lungs try to correct it. Whatever is not damaged is whatever will kick in to try to compensate it. Please, if you have any questions about that, shoot me an email. That's a tough one. Okay, when discussing primary and compensatory regulations of pH, A patient will expire more CO2 when their body is too acidic. B, a patient will take less frequent, shallower breaths when acidic. C, a patient will excrete more bicarbonate ions in their urine when acidic. Or D, none of the above. So I made this a little bit more of a difficult question because I really want to know if you understand these concepts. Metabolic acidosis. This is a deficiency of bicarb or an excess of hydrogen. This can also be with ketoacidosis. Okay, so ketoacidosis is when insulin is insufficient or not functioning well. So we can either have a lack of insulin or insulin receptors on cells do not work efficiently. When we ingest glucose and it gets into our bloodstream as dextrose, our whole goal in releasing insulin or injecting insulin is to bring glucose to receptors on cells, and the receptors on the cells need insulin with the glucose in order to get glucose into the cells. So with diabetes, either we have insufficient insulin, where we don't secrete it from the pancreas, or it doesn't function well at those receptor sites of cells. If we can't get the glucose in through those receptors into the cells, it'll just stay in the bloodstream, and we increase serum levels of dextrose or glucose, okay? So if we have it out in the bloodstream, we can't use it. It'll stay in the bloodstream or it'll be dumped through the kidneys. If that happens, what we turn to next for energy is fat. And fats are released, and the liver needs to convert them into, or partially convert them into energy. If we have too much fat, the liver can only convert so much of that fat into energy, and the rest are turned into acid called ketones. Now that's difficult. If that's difficult for you, rewind back and listen to it a couple times. So the byproduct of this inefficiency is ketones, leading to ketoacidosis in the bloodstream. Ketoacidosis increases the acidity or lowers the pH in the body. Patients will have excessive urination due to that glucose dumping. And actually what will happen is some of those ketones are turned into acetones. And the acetones are excreted through our breath. We have acetones in nail polish remover, which creates kind of that fruity smell. And we get that same kind of smell. Well, I don't know if it's really comparable, but you get the idea coming out of that patient's breath. Shoo! All right. So metabolic acidosis can be via ketoacidosis. I'm not going to repeat that because it was such a long little explanation, but if you have questions, get a hold of me. Or we can have a deficiency of bicarbonate or an excess of hydrogen due to some sort of kidney issue. Now, anion gap. I have a video that's kind of long for this because I think this is a little bit difficult to understand. But don't let this blow your mind, and if you just have the basics of this, that's all we need to know. So the basic gist of this is we have so many positive ions that we're going to measure and so many negative ions that we'll measure in the bloodstream that are normally there. And there are some unidentified negative ions that can actually contribute to the overall number of negative ions. Oh, this is very confusing. I have a good graph that I'll show you in just a second. That is the anion gap. Okay, so here, let's look at the next slide. So normally the sum of the positive ions, which are your cations, should just about equal the sum of anions or the negative ions in the extracellular fluid. So sodium is going to be the most plentiful positive, okay? Bicarb and chloride are the most negative, abundant negative ones. That anion gap is going to be any excess ions that we'll see other than bicarbonate and chloride. Okay, a normal anion gap should be about 6 to 9 milliequivalents per liter. So if we look at this little chart, this may be a little easier to understand. So if we have an excess amount of unidentified ions or negatively charged ions when we're looking at the whole. So we're looking at the whole amount of ions in the extracellular fluid. Sodium will be the majority of the positive ones. Okay, chloride should fill about this much. Bicarb should fill about this much. If we have excess amount of unidentified negatively charged ions, it will decrease the amount of bicarb and create a more acidic environment. Okay, don't think because this is a negative charge, this means this is an acid. Okay, it's bicarb. So this is the bicarb ion. Okay, so in the normal body fluids, we have a certain amount of sodium, a certain amount of chloride, a certain amount of bicarb, which is HCO3 negative. If we get too many unidentified acids, we can increase this anion gap, decreasing the amount of bicarb, creating a more acidic environment in the body. Oh my gosh, I know that's so confusing. Okay, so if we go back to this slide, so normally cations should equal the amount of anions in the extracellular fluid. Okay, if we get too many acids, they will actually take up some of that space. Okay, and that will create that anion gap. You know what? Don't let this blow your mind. What I'm more concerned about is you remembering metabolic acidosis, okay? And remember the kidneys and their balance of bicarb and hydrogen, and also ketoacidosis. The only reason I will never test you on anion gap, because I think it's very confusing. I'm just wondering if you might see this on your boards. So what I'm going to ask you to do is to remember that the normal anion gap is 6 to 9 milliequivalents per liter. If you have a bigger one, that means you're going to have more acids in the extracellular fluid. Let's keep it to that, okay? And of course, if you have questions, I'd be happy to help you. And hopefully that video is helpful too. So metabolic alkalosis is when the kidneys retain bicarb or get rid of hydrogen. Okay, it's as simple as that. Question time. Metabolic acidosis could come from diabetic ketoacidosis. Easy peasy. True or false? So respiratory acidosis, bam, you should know this, is when we retain carbon dioxide. Okay, hypoventilation or decreased gas exchange, such as our COPDs or emphysema. Respiratory alkalosis is when we get rid of too much carbon dioxide. This could happen with acute anxiety, pain. I remember this happened when I was playing soccer when I was a little kid, and I twisted my ankle and it hurt so bad I kept breathing so much. So they actually gave me a brown paper bag so I could retain the carbon dioxide, right, and decrease my respiratory alkalosis state. Mixed disorders gets crazy, all right? And generally, if you're getting somebody who's getting to the point where they're getting a disease that's causing them, say, respiratory alkalosis or acidosis, guess what? The kidneys are probably going into acidosis, alkalosis as well. So you're going to have to look at your blood gases, which we're going to get into in just a second, and do your best to guess at what's happening there. Okay, so acid-base imbalances, once again, if this chart helps you, fantastic. If not, I'm taking all my questions from the lecture notes themselves on the PowerPoints. And this can show you how there's different diseases which can cause some crossover with those, but once again, I'll test you on what we got in the notes. So a patient can only have respiratory acid-base imbalances or metabolic acid-base imbalances. They never have a mix. Pretty obvious. True or false? Okay, so ABG interpretation. I have another video for you for this because I could imagine that on your boards you would have questions for this. You're going to look at pH levels. So that'll be that serum hydrogen concentration, which is your 7.35 to 7.45. Partial pressures of CO2, which is going to be your partial pressure of carbon dioxide. That'll be, the partial pressure simply means the pressure that it takes to put carbon dioxide into the bloodstream, but it indicates the levels of carbon dioxide in the bloodstream. And a higher level will be obviously a retention of carbon dioxide, and a lower level will be an excretion of it. Bicarbonate, don't forget that I told you that bicarbonate measures the activity of the kidneys, either retaining it or excreting it. If you're excreting it, don't forget bicarbonate makes you more basic. So if you're excreting it, you're going to be less basic, which means more acidic. If you're retaining it, you're going to be more basic. Okay. Partial pressure of oxygen is going to be the serum oxygen concentration. That won't obviously reference the pH as well, but excuse me, they have it listed for you. And here's your normal values. Okay. And those should look pretty familiar, I would think. So ABG interpretation. Excuse me. So respiratory acidosis will create, more of an acidic state in the body, and that'll be driven by the retention of that CO2, as opposed to alkalosis will be more basic. You'll be getting rid of that CO2. Metabolic acidosis will have a normal bicarbonate, but I would think you'd also get rid of bicarbonate if that should happen. And metabolic alkalosis is going to be when you retain it. So I know it says normal, but bicarbonate levels will also affect your metabolic responses. So if this chart helps you keep it. Oh, there we go. PCO2. I'm so sorry. I'm reading the wrong thing here, thinking the book is wrong. Here we go. Dr. D's getting tired. Okay. Here's your bicarbonate levels. I don't know. This is wrong, guys. Okay. This is wrong. So with metabolic, this should be CO2, guys. They have it written in the wrong space. And I thought it was either A, losing my mind, or B, the book had it wrong. they do. Please cross this off if you're going to study from this and put CO2 here. Okay, so if we're talking about metabolic, CO2 will be normal levels, which they have correct as normal, should be CO2 though. But bicarbonate in metabolic acidosis would be too low. Metabolic alkalosis would be too high. Okay, and what they're saying over here with compensation is simply the lungs will compensate for metabolic, right? And then the kidneys will compensate for respiratory acidosis or alkalosis. And that compensation comes in with carbon dioxide, right? You'll try to retain carbon dioxide if you have a metabolic alkalosis. If you have a metabolic acidosis, you'll try to get rid of carbon dioxide. Complicated, isn't it? With a respiratory alkalosis, your body is going to try to get rid of bicarbonate through the kidneys. With a respiratory acidosis, your body is going to retain bicarbonate to fight that acidosis in the kidneys. Holy crow, that is complicated. I hope it makes a little bit of sense. If it doesn't, you're going to have to review my acid base lecture as well. It's only 10 minutes. And after you review several times, if you still have questions, let me know. Once again, don't forget to correct under PaCO2 where it says normal bicarbonate. It's not bicarbonate. It should say CO2. I apologize for that, but I didn't make that chart. Just saying. Normal. Here's an easy question after all that craziness. Normal systemic pH is between 7.35 to 7.45. You are welcome. Have a great day. Please, this is the lecture that always makes me exhausted because it is so complicated. If you have any questions, by all means, write them all down and shoot me an email, or I'd even be happy to call you and walk you through anything if you need it. This is Dr. DeChavo at the end of Chapter 6. Thank you and have a great day.